Okay, let's start. So I gave you guys 2 handouts. You're supposed to have 2 handouts, so count them. We're going through the first one only because I didn't get to the second one. So we're going to be doing marginal functions. I'm going to do one more example on linear approximation, then we move on to marginal functions. Should be a short class because I know I said that last time, but I'm pretty sure it's going to be short this time. Because I ended 5 minutes earlier in my other class, and that was after there was this whole mystery at the first part of the class that we're all trying to solve, and then somehow we ended up talking about Super Bowl commercials, and I don't know.
What was the mystery?
No. Wait, what was the mystery? Oh, because we want to get out.
Yeah. Never mind.
What? Does anyone know who Soy Boy is? Is that a thing?
Soy boy?
No.
Soy Boy.
Yeah, I don't know.
Wait,
Julius told me to write that on the board when I came in, and I was like, Julius, I don't know what you mean.
Wait, wait, okay, so now, okay, wait, who's Julius?
Julius is in your class.
Romero.
Yeah,
I
class.
He told you to write it? Julius from my class?
Yeah.
From the other class? Julius?
I mean, do
Julius? Julius told you to write it.
you
Yeah, I don't know.
Julius,
Yeah, I was
though?
like, I don't want to. I don't know what that is. Wait, what's soy boy? I don't know what that is.
I don't know.
What's the big deal about
It sounds like
What's the big deal about soy boy? Yeah, I'm confused.
Like every time I show up to that class, someone writes Soy Boy on the board. And they don't just write Soy Boy. There's like, they do this whole thing where like, do that, and then they write Soy Boy. like big, it's like right in the middle of the board. And it's like every time, I'm like, who is this Soy Boy? Every time I come to class, there's Soy Boy there. And then,
I think Julius would do though.
so y'all know Julius? But then that reminded me of this other mystery that was in the math department. We have a whiteboard in the back of the math department that every Monday you come in, someone draws this artistic masterpiece on the whiteboard in the math department. And everyone's like, who is doing this? Who breaks in here on Friday night?
It's Soy Boy.
It's Soy Boy.
No, they had much better artistic skills than Soy Boy. Like, I'm not kidding, it's like crazy. It's like Goodwill Hunting. Like this is this week's drawing.
Oh, that's really good. Oh, wow.
Like on a whiteboard, they do this.
Have you asked anyone? Like any teacher?
No one knows. I've been asking
Right on
around.
the whiteboard, who are you?
I did. They don't answer. I'm like, who are you? This was the previous week.
What? Wow.
The-
really good.
Let me see.
This was the previous week.
Whoa!
Like, I'm not kidding. It's like some serious. Like they must have took hours to do this. It's big. Like they use a lot of marker.
Probably like a janitor.
Ooh, it might be Jhevon.
Yeah, like Goodwill Hunting.
Yeah.
That's what I'm thinking. But
It's Goodwill Hunting. Yeah.
like every Monday you show up to the math department, there's a different one of these on that. And no one knows it's who. We're like, who are you artist? Who is the whiteboard artist? And there's this big mystery. Then I come to my class over here. There's Soy Boy on the board. I'm like, what is going on with this place? I thought it was a janitor, but I don't think it's a janitor because there was no drawing during like a week or two ago when there was like
Julius?
when there was like
Because he's texting me now. I swear to God, I didn't nothing.
Okay, this is
wait, is Soy Boy watching us? Like, what is going on?
Somewhere in this room texted Julius. So who read it? Yes. He's like.
I was like, bro, they just exposed you.
Okay,
Like,
okay.
It wasn't me.
Minus 10 points. Don't.
That's my boy.
He said it wasn't him.
Oh. I'm gonna text you like, why did you say that?
I don't know. I'm gonna get to the bottom of both of these. But I now think it's a student doing the drawing on the math department. Because during like that week where everybody had like 5 midterms, there was no drawing that week. So I'm like, why are you suddenly busy now? Of all times. You know, now I think it's kind of a student. But I will find them. To like set this camera up in like a corner or something. Just have it running all weekend. With a live feed.
Expose them. That'd be hilarious.
if the RAM covered that, that would be hilarious. they might contact you in the next week.
Investigative journalism.
Yeah, like we need to get to the bottom of these things.
And the Julius is all caps now. Sorry, man, I didn't know.
Okay, let's get to. I don't want this to go back spiraling. Talk about commercial. Anyway, so linear approximation is what we spoke about last time.
I'll just watch this part.
So let's recall what linear approximation is about. We had a formula that we developed by using the tangent line. This told us that for a function, we could approximate it with the expression. Do we remember the expression? Linear approximation formula.
F of A, F prime of A,
Plus
X times A.
times x minus a. That is something I will expect you to memorize, so it's a very important formula. What you can realize is that the left side is just the tangent line. If you did y is equal to f of a plus f prime of a times x minus a, that actually gives you the equation of the tangent line, right? That's the point slope form for the tangent line. Right? This is the line through the point a comma f of a with slope f prime. But that gives you, that's like your m times x minus x1 equals y minus y1. So it is just the equation of the tangent line. And we end up with this formula. When is this formula good to use? When does it give you a good approximation? What's a kind of rule of thumb here? Yeah?
When A and X are really close together.
When x and a are close together, right? So x is close to a. Right, so if these 2 points are farther apart, it's not necessarily a good approximation because you can have a function doing its thing, and at a point, if you go out far into the future, the difference between the tangent line and the function are huge, but the closer you get to the point itself, the difference between the tangent line and the function are small. So it's a best used when you're pretty close together to the point of reference, and it will be approximate. And of course, your f is differentiable and all that. So if your f is differentiable and your points x and a are close together, you can use this expression to approximate the output of the function. Okay, and I actually did this by hand to approximate the square root of 3.99, and we were correct up to like 4 decimal places after rounding, and we did that by hand in our head. So it's a really powerful technique. So I want to do another example like that, because it is a kind of question that I would ask you. Approximate this thing using linear approximation. This is the kind of question that you can expect on future tests and quizzes. So let's actually run through one more example. And I'll kind of have you guys take the lead on this one and sort of tell me what to do for a second, third, to kind of figure this problem out. So, approximate the cube root of 8.01 using linear approximation. Okay. So that would be the question. Okay, go. Now what? Yeah?
Can you say that it's close to like 8 and you can find, actually no, you can't find the cube root of 8. Yeah, and then based on that, like use the linear approximations.
Sure, but for the linear approximation formula to work, we need some function, right?
So
probably the first thing I would do is figure out what function I'm going to use. So the first thing we would do is define our function. So what do you think is a convenient function here? Yeah?
cube root of 8.
Cube root of 8 is a number.
Oh, x.
So cube root of x would be a nice function to use. You obviously want the value of this function when your x is equal to 8.01. But that's your general function that you want to do, right? So we know from the linear approximation formula that we're going to have to use the derivative at some point. So once we find our function, we would find the derivative. So in this case, what is our derivative?
Root of that.
Yeah, so you differentiate it. How would you do that?
1/3 x to the -2/3.
Right, you think of this as x to the 1/3 using the laws of exponents, and then you do the power rule, you get that, which you could write as this, but it's not super necessary. That's cube root of x squared. So you find the derivative. So we know we're going to use these guys in the formula, but what are we going to plug into the formula? That's what we would probably figure out next. So here, well, I don't, find is a strong word. You don't want to find it, but x add a. So here, what would you say x is equal to? What would you say a is equal to?
X is 8.01 and then A is 8.0. Like what's closest to it? A. So 8.
8, right? So remember your x, your a should be something that's close to the x value, but it's a very nice value. It's a value that you know all the information for. Cube root of 8, we know that. That's not something difficult to do. So your x value is the value that you want to approximate your function as, but the a is going to be a nice value close to that you already know all the answers for. Right? So at this point in time, you have all that information. You want to just move a little bit into the future and see what's going on. Yeah.
What if you have something else other than 8? Like what if you had like a number like random, like some other number, like would you?
Yeah, like 27 is also something that we know a cube root for.
Yeah.
But why would I not pick 27 as opposed to 8?
Because it's not as close.
It's not as close. So that's one of the, in the theory of the linear approximation world, that's always a consideration. You want to get as close to the thing as possible. So while there are many other numbers that I know the cube root of, I wouldn't pick any of them because 8 is the closest one. Right? And this really works when the approximation is close. Okay. So yeah, 8 is the best number to choose here. It's the closest thing to 8.01 that I actually know the cube root of. So let's actually, so now we can actually plug into the formula. That's the fourth. Plug into formula. So we know that the formula is f of x is approximately equal to f of a plus f prime of a times x minus a. So this means the cube root of 8.01, well that's just f of 8.01, but I know that's roughly speaking equal to this expression, so that's going to be f of what? F of 8.
Prime of 8
Prime of 8.
times x minus 8.
Well, I know the x.
8.01.
Yeah, so that's 8.01 minus 8. Now let's actually plug in the pieces. What is f of 8? So remember my f of x is the cube root of x. My prime of x was 1/3 times the cube root of x squared. So that's my function. What is f of 8?
2.
It's just 2. Plus what is f prime of 8? Plug that in here. So you plug in 8, take the cube root of that, you get 2, you square that, you get 4, multiply by 3, you get 12, plus 1/12. And this is just 0.01 positive. And so this is really 2 plus 1/1200, which is plus 2 plus 1/1200, that's 2400 plus 1, 2401/1200. What is that roughly? it's definitely 2 point something.
2.0000833.
And I think the 3's would
Yeah.
repeat forever. What is the actual answer? So if you plug into your calculator the cube root of 8.01,
2.000832986.
so if I round it to here, that would actually give me that. So that's 1, 2, 3, 4, 5, 6 decimal place accuracy when I round. Not bad. Now the idea behind this being is that sometimes working with the tangent line is easier than working with the original function. And we're kind of going to see that a little bit with the next topic with marginal functions. So we're going to use the derivative again in somewhat a similar capacity, but not exactly with marginal functions. But that's all I wanted to do for linear approximation. If there's no questions about that, we'll move on. So now you can turn your attention to your handouts. We're going to talk about marginal functions. A marginal function is actually another synonym for derivative. So we know that if f of x is a function, then f prime of x, right, as long as it exists, is called its marginal function. In some contexts, particularly in economics, business context, we use that language, the marginal function. So we can have functions that measure, for example, cost and profit and revenue, but we can also talk about the marginal cost, the marginal revenue, the marginal profit. So that's an example here. If c of x equals your cost function, then c prime of x, if you can somehow determine that function and take its derivative, this is called a marginal cost function. So in order to find the marginal cost, I need to first know about the cost and I take the derivative. Similarly, to find the marginal revenue, I need to know about revenue and take its derivative. To find marginal profit, I need to find profit and take its derivative. Right? So that's what it's called, marginal cost. And that language kind of talks about what's happening at the margins. So in what sense? So why is this useful? If I know my cost function, what benefit is there to talk about the derivative of the cost function? Well, let's go back to what the derivative told us about. We know that c prime of x by definition is the limit as h approaches 0 of c of x plus h minus c of x over h. This means if h is small, right? We know our h is approaching 0, so our h is getting smaller and smaller and smaller and tinier, right? If h is small, what we're saying is that c prime of x will approximately be equal to this expression. That's in fact the linear approximation formula, but I'm using a different notation. Now suppose the following. Suppose we're in a context that x is large enough, so large that h equals 1 can be considered small. So again, this often comes up in like economics context, so we might be talking about X is the level of production of some large company or large factory or something. So we're producing thousands upon thousands of units, tens of thousands, hundreds of thousands, right? So we can talk about X being the number of iPhone X's that were produced in 2017 or something like that. Right? So this is a huge number to the point where one iPhone is not that much compared to all the number of iPhones. In fact, one iPhone is literally the smallest number you can get. It is as close to 0 as you can get if that is the function you're considering. Right? But if you're in a situation where the number 1 can be considered very small, pretty much as close to 0 as you can get, then you can just plug in 1 into that formula over there for H, and you get this expression. And that's kind of the expression that's important to us. For example, how could you interpret the right side of that expression? How could you describe that expression in words? If I say C of x plus 1 minus C of x, what am I talking about? What does that quantity mean? So let's say C is my cost function. What can I interpret this expression to mean? Yeah?
Like it's just your difference of cost from one value x to the next.
Right. Or I can think of it as the additional cost of producing one more item, would be another way to phrase that. Right? So you could phrase this as, for example, the additional cost by producing one more, specifically one more item. Right? So this is the cost to produce X items. This is the cost to produce X plus 1 items. What is the difference in that cost is just how much extra would it cost me to go from X to X plus 1? Right? So this is like someone asking, if we produced 1 million iPhones, how much would it cost us to produce 1,000,001 iPhones?
Is this like value of marginal product?
So that's like yes, like, what? What did you say?
Like marginal product.
Similar.
Okay.
Are you talking about it in economics class? Are you taking an economics class? Or you took it a long time ago?
Yeah.
Okay, but yeah, usually when they use the word marginal, this is kind of what they're talking about, like a little bit extra. What would happen if we kind of push the envelope a little bit more? Which is not exactly a trivial question to ask. It's not always clear. Your cost doesn't always just move up. Sometimes it can not even move at all from one product to the next in theory, right? So if you're paying rent for a space, you're hiring a certain number of employees, then really it's not going to take you that much extra to produce one more item in general. But it could be the case that, oh, you're at max capacity, right? And your workers literally can't do it anymore. So to produce one more item, you really have to open a whole other factory and hire a whole, So there are times when the cost can like jump or spike, and there are times when it won't jump at all. But usually if you sort of can be tracking things very carefully and you're keeping close tabs on your data, you can sort of talk about this as the marginal cost. How much would it cost us to go a little bit extra, produce one more item? What would our situation look like? And you can talk about that sort of scenario with profit, with revenue. If we produce one more item, what would that do for our revenue? If we put one more item, what would that do for our profit? How does that affect our costs? How does that affect this? So that kind of comes up in planning scenarios when you're sort of planning something. You can actually use the derivative to describe what would happen if you just go a little bit further than you're currently going. Right? So that's the interpretation. So that's why marginal functions are very useful. They're useful at your margins when you just want to push it a little bit more and sort of tiptoe and see what's going to be happening. You can actually use the derivative to describe such a situation. So let's actually do an example. So the first example is just getting you used to this idea so you can actually compare what I'm talking about. So in example 1 on the second page is going to be, I'm going to ask you to do something 2 ways. Actually compute the additional cost and then use the marginal function to approximate the additional cost. So let's actually do that. This is example 1. So we're told the cost of producing X glow in the dark boxer shorts is given by that function. Right? Now cost functions aren't really something you can derive, they're just something that comes from statistics. It depends on the particular cost of the scenario you're in. So it depends on how much you're paying for rent, or how much you'd have to pay in salaries, or how much it costs you to find workers and all that stuff. So this is really something that really statistical data is what would get you to this function. Right? Or some approximation of it. So you can sort of get a function that tracks how much things are costing. So let's suppose this is the cost function for producing a certain item. So I can talk about how much would it cost me to produce one of these items. Well, it would cost me $5, right? Because I plug in X equals 1. Or $5,000, depending on the units. How much would it cost me to produce 2 of these items? You plug in 2. Right? So that would give you 8 plus 6, so that would be 14. So to produce 2, it will cost me $14, right? And so on and so forth, right? So this is a function that tells you what is the cost of producing this number of items, okay? So now let's look at the 2 questions. What is the additional cost to raise the production level from 10 to 11? So let's pretend that we've already produced 10 such items. How much extra would it cost us to produce one more item, the 11th item? So what would that be? How would you figure out the additional cost to produce from 10 items to 11 items?
You just plug it in and then subtract.
Just plug them in. So what would you plug in? So this is
Wait,
CF what?
11?
CF 11 minus CF 10. Yeah, that's the cost to produce 10 things. This is the cost to produce 11 things. Let's find the difference between them. And so what would that look like here? That would be 2 times 11 squared plus 3 times 11. Minus 2 times 10 squared plus 3 times 10 equals, what's that?
45.
Huh?
45.
45. Some expensive boxer shorts. So if I produce 10 of them, the additional amount it would cost me to produce one more is $45. Let's actually go to part B now. We're going to compare this with the value that the derivative gives us. So the approximation probably won't be that good because x isn't that large. I mean, 1 compared to 10 is not that small. But let's actually do it anyway. So in B, we were asked to find the marginal cost. When x equals 10. So what is that going to be? So that's C prime, that's the marginal cost.
4x plus 3.
That's 4x plus 3. This is your marginal cost. So what is the marginal cost when x equals 10?
43.
You just plug in 10. So that's 43. In other words, that would be my guess, right? One thing you can notice right away is that look at the expression you had to compute to find that answer directly versus the expression you had to compute using the derivative. This one is a lot simpler than that one, right? And cost functions in general can be very complicated. This is a trivial Mickey Mouse example here. But the thing is, I wasn't actually off by that much. Using the derivative to track the cost, I would have guessed it's going to cost us around $43. It'll actually cost you $45, but that's not a bad guess. I'm off by 4%, and I'm not even talking about a huge number here. That's just with 10, and I can get a pretty good approximation with this particular function. So that's sort of what the derivative is supposed to do. It's supposed to kind of give you an idea of the additional cost of producing one more item without having to go through a whole lot of trouble. Okay, let's go to the second example, which is a bit more involved, and I'll probably have to define a lot more stuff in order to get through it. But in this topic, a problem I might give you on a quiz or a test would probably look more like example 2, right? So I'm going to ask you to do a bit more of that and ask you about interpretations and things like that. So let's look at example 2. We'll define some functions as well as we're going forward. The examples here are usually going to be business related. I know not most of you probably aren't business majors, but it's one of the applications. Example 2. Suppose a demand function for a product is this function. So we have a demand function. Is P is equal to 25 over square root of x. Do we know what a demand function is?
How much people demand something?
Yeah.
But in a business context, what would that function represent to you? What do you think that is? P equals 25 over radical x. P is very suggestive here, though. What do you think P stands for here? Yeah?
Price.
It's price, right? So that would be the price that I could charge for selling X items. But that is based on something called the demand function. So this is just a function that describes how much consumers are willing to purchase at a certain price. There's also something called a supply function. This is how much producers are willing to produce at a certain price. So like in an economics context, if I'm plotting price on the horizontal and say the number of items either sold or produced on the vertical, it turns out that a demand function will always be a decreasing function. Why? Because as price increases, people will buy less, right? People buy more Toyotas than Ferraris, because Ferraris cost more. Right? So the higher you raise the price, the less willing people will be to buy it. So whatever function this is describing what your consumers are willing to pay, how many of a product a consumer is willing to consume based on the current price. So when I say a demand function, this is the price that you can reasonably demand from your customers. Okay, so that's what the demand function is. Supply functions always sort of increase. If I can charge more per product that I'm producing, I'm of course going to be willing to produce a lot more because I'm getting more money as a result of it. If I can produce 5 things at $2 each, I'll probably call in sick. But if I can get 100 each to produce 10 items, you'll be better believe it, I'll be willing to get out of bed more, right? So producers will be, as the price increases, producers are willing to supply more, but people are willing to purchase less. The goal of any business would be to try to find this sweet spot right here called the market equilibrium. Right? So that's the price that a supplier can charge where they know that they will sell the maximum number of products, and they don't want to really pass that point because then they'll have a bunch of supply that no one's buying. Right? And they don't want to be below that point because then they're leaving money on the table. So that's kind of the idea. So the demand function is really describing the price you can charge for something reasonably. So I know that if this is my demand function, to be able to be sure that I can sell 100 items, I should charge $2.50. Right? So if I know the capacity of my factory is that we can build 100 items, what price should I charge? According to this function, $2.50 per item would be the price I would charge. Right? And again, this comes through market research and statistics. That's why statistics and probability are also important. It's not just calculus. But yeah, you do your research and you kind of, offer two different prices for the same thing in different regions and that are similar otherwise, and kind of see how many people are buying it over here, how many people are buying it over here. You kind of do this research and you would come up with this function. So that's your demand function, right? So that's the price you can reasonably charge for something. So now that brings us to part A. Part A asks us, find the marginal revenue. In order to find the marginal revenue, what do I need to find? Yeah?
To find how much, well, revenue's not profit, right? So
No. What is marginal revenue? Yeah?
This is like approximation of the revenue, or no?
Not an approximation of revenue, no. Think of it in terms of the kind of function. What is it?
This is like marginal revenue kind of describes how much money you're gonna make for each additional product that you're making.
Correct. That it would be a description of that. That's true. Mathematically, if I were to write that down as a thing, what would that thing be?
Would it be derivative?
It is a derivative of
The function
of the revenue.
revenue, yeah.
Right. So there's an interpretation that goes along with it, but if you just want to find it, you need to know it's the derivative of the revenue, which means if you need to find marginal revenue, you first need to find revenue. Now, given the fact that this is how much I can charge, what would my revenue function be? Yeah?
Price times how much you sell.
Exactly. X times P. This is a formula that you can now know, right? We've seen formulas like this when we were doing Jhevon's hot dog stand at the very beginning of the semester. Things are coming full circle. So now let's specify that. So the revenue is the price you can sell an item for times the number of items sold. So this is talking about number of items sold times the price per item. Price per item is given by the demand function. Right? That's you tracking how your customers' spending habits and know this is the price they are willing to pay for me to sell this many items to them. Okay, so that's your revenue function. So in other words, specifically, what is my revenue function in this case? Yeah?
X times 2S.
X times this. Can I simplify that?
Get the radical out of the bottom.
And
So, is that 25x squared over x? Wait. Actually, I don't know.
25x radical x.
Wait.
25 radical x.
Oh, okay.
Oh yeah.
Yeah.
I was almost there.
There are tons of ways you could have done that. X over radical x is, you know, that's x to the 1 over x to the half. Subtract the powers, you get x to the half. You could also think of, since your x is positive, this is just radical x squared. So you divide it by radical x, they cancel. You can also do the thing where you rationalize, multiply by radical x over radical x. This creates x, which cancels, and you're left with there. Tons of ways to get it, but that's what it was. So that's our revenue function. So now we found the revenue function. We want to find the marginal revenue function. What do we do? So that's the derivative. So the marginal revenue is our prime of x, which in this case, just find the derivative of this. That's 25 times 1 over 2 radical x. So that's my marginal revenue function. So this is my demand function. That function will describe my marginal revenue. Let's move on to part C. Which I'll probably need more space. Part B. What is the marginal revenue when x equals 100? Yeah?
Just plug x.
Just plug x
Yeah.
equals 100 into
Yeah.
that. This is talking about r prime of 100 equals 25 over 2 radical 100. This is 25 over 20. That's what? 1.25. And it says, interpret this number. What would your interpretation of that be? Let's say the units here is in dollars. What would that mean? What does that mean to you? That r prime at 100 is equal to $1.25. What does that say?
Bringing in another $1.25 if you were to make one more, whatever you make.
The additional revenue what we're saying is after we've sold 100 items, if we were to sell one more, the additional revenue we bring in would be $1.25. Gained by selling the 101st item. So in this case, I can pretend we've already sold 100. How much additional revenue would we gain by selling one more item? $1.25 is how much we would gain. C. Here we're given the cost function. Right, so we're talking about the same item here. We're told the cost function is x squared plus 2x. Right, and again, unlike revenue, there is no general formula for the cost function. As I said, it really depends. It's more of a statistical question than something you can derive mathematically. But for this product, we know that's our cost function somehow, through just collecting a lot of data and analyzing it. We figured out that that was our cost function. So now the question is, what is the marginal profit? So in simple terms, what is marginal profit? Yeah?
Marginal revenue minus marginal cost.
Oh, well, for that you need to know what profit is, right? So first marginal profit is the derivative of profit, but profit we get by?
Revenue minus cost.
Profit is revenue minus cost, right? So it's how much money you're making subtracted how much money you spent to make that. And so this is what's left over. Right, so that you talk about as your profit, like that's what you actually take home. right? After you pay your taxes and your employees and rent and all that stuff, this is how much money you'd end up with. So profit is the thing you're really after. You want to maximize your profit. So you do want your revenue to be larger than your cost. Profit is something you always want to be positive. And so this means that marginal profit, which value? So this is a general formula that you can take into account. If you want to reinforce the fact that revenue is X times the number of items sold, you could remember the formula is this, X times P minus C of X. So that would be your profit function. The marginal profit is just the derivative of that. And using the sum rule, it's exactly as you said. It's just the marginal revenue minus the marginal cost, because the derivative of this is just the derivative of each individual. This means marginal profit equals P prime of X, which is just going to be R prime of X minus C prime of X. But anyway, let's continue here. Here, what is our profit function? So profit equals revenue minus cost. So revenue was what?
X 25.
Oh, 25x.
Square root of x
25 squared of X was the revenue
minus
minus.
X squared plus 2x.
Again, be careful here, parentheses. That's going to be our profit function. So this means marginal profit equals P prime of X, which is
2 square root of x minus 2x plus 2 parentheses.
but that would be it when we get it out of parentheses.
Oh, yeah.
And so, what did they ask for? It just says, what is the marginal profit function? That would be your marginal profit function. So let's move on to D. So what is the marginal profit at the production level 100?
Plug it in.
Plugging 100. It's not done. I mean, once you know the formulas for all these functions we're talking about, it's kind of just plug and chug. You find knowing when to find derivative and when to plug in the number. The cost function always have to be given to you. That's not something you can figure out. But revenue you can figure out, and profit you can figure out given other information. But yeah, so this is just P prime of 100. This is just me plugging in 100 here.
Oh, yeah. Oh, you just said
What is that?
Negative 200.75.
Which brings us to the last question. Is it worth producing one more item?
No.
Clearly not. In fact, you should have stopped producing items a long time ago. At this point, the next item you're producing, you're losing 200. That kind of hints to you that you've probably been losing money for a while. You probably should have stopped a long time ago. The answer is no. Expected profit is negative. Right? This means clearly your cost will exceed your revenue. Yeah.
Wait, so what's the interpretation of negative 200.7?
That means if I produce one more item, so pretend we've already produced and sold 100. If I produce one more, the profit I can expect is that number, which is negative, which means I'm actually not making money, I'd be losing. In fact, to produce the 101st item, I would lose $200 by making that decision. that means I've been selling more than I should be selling for a while. At that point, my costs are growing too much, and it's eating into my revenue. So yeah, if there are no more questions, we'll stop there. So homework for 3.5. Homework for 3.4 and 5 due today. This is all we are doing for 3.2, so that homework is due on Tuesday, and we'll stop it. So now we know who Soy Boy is, if now we can only find the whiteboard artist.